The moon looks close and familiar, but living there would be far harsher than most people think. Gravity would change your body, time would stop feeling normal, and every step outside would become a survival task. This is what life on the moon would really be like, when the excitement is over and the danger becomes everyday life. The moon is close compared with most places in space. On average, it is about 384,400 kilometers away from Earth, or 238,855 miles. Apollo crews made the trip in roughly 3 days. That sounds short until you translate it into human reality. On Earth, an emergency usually means help in minutes or hours. On the moon, a serious mistake can leave you waiting days for any outside help at all. There is no fast rescue, no quick evacuation, no simple resupply. If a medical problem starts, if a machine fails, if a leak appears, you're not dealing with a delay. You're dealing with the fact that Earth is still almost 250,000 miles away. That is close enough to talk to, but far too far to depend on in a crisis. So does the most dangerous part happen before you even touch the ground? Not exactly, because landing itself is already a very unforgiving process. A lunar landing is not like landing an airplane. There is no useful atmosphere to slow you down. No parachutes, no wings, no aerodynamic braking. Every bit of speed has to be removed by propulsion. That means the spacecraft has to lower itself onto the surface using rocket thrust alone. And it has to do that while dealing with dust, glare, limited visibility, and hard vacuum. The moon's gravity is only about 1.62 meters per second squared, around 1/6 of Earth's gravity, but that does not make the landing simple. A lighter pull does not erase motion. The vehicle still has mass. It still has momentum. If it is descending too fast or drifting sideways, weak gravity does not save you. It only changes the numbers the pilot or guidance system has to manage. You're still bringing down a heavy machine under precise control, and any error at that point can end the mission before life on the moon even begins. And then comes the part most people think would feel easy. It would not. Your first step on the moon would feel physically wrong in ways training cannot fully prepare you for. Your body weight would drop to about 16.5% of what it is on Earth. An 80-kilogram person would feel more like 13 kilograms there. A 176-pound person would feel closer to 29 pounds. That sounds like it should make movement simple. It does not. Your mass stays the same. That means once your body starts moving, it still resists stopping in the way mass always does. So on the moon, you feel lighter, but not more precise. You can push off the ground more easily, but you also spend more time off the ground than your instincts expect. You can start moving quickly without meaning to, and then it becomes harder to correct cleanly. Apollo astronauts learned this almost at once. Normal walking was not very efficient, so they shifted into hopping and loping because the moon forced them to. That is a strange thing to realize. Even the simple act of moving from one place to another stops working the way your Earth-trained brain expects. You're lighter, but not safer. You're slower to fall, but not necessarily better balanced. The moon takes away some weight, but it does not take away the consequences. So maybe the moon still feels manageable because Earth is right there in the sky. That is another trap. From the lunar near side, Earth would look close in an emotional sense. You would be able to see home as a real world hanging over you, not as a distant point of light. Communication would also make that closeness feel even more real. The signal delay is only about 1.3 seconds one way, about 2.6 seconds round trip. That is small enough that people can still talk to each other in a mostly normal way. You say something, there is a short pause, and the reply comes back. It still feels human. It still feels connected. But logistics do not work on conversation time. A voice can reach you quickly. Emergency equipment cannot. Spare parts cannot. Surgeons cannot. Rescue crews cannot. So the moon creates a very specific kind of psychological pressure. It makes Earth feel present while also making it unavailable. You would feel connected and isolated at the same time, and that's a difficult thing for human beings to live with day after day. And that leads to the biggest correction of all. Most people treat landing as the climax. On the moon, landing is only the start. The real story begins after touchdown, when every system around you stops being background technology and becomes part of life support. Air is now something a machine has to provide and protect. Water is no longer just water. It is supply, recycling, hygiene, cooling, and survival. Thermal control is not comfort. It is the reason your habitat does not overheat in sunlight or freeze during darkness. Power is not a convenience. It is the thing that keeps your air systems, filters, communications, computers, pumps, and medical equipment running. Radiation shielding matters, dust control matters, waste recycling matters, battery storage matters, door seals matter, suit joints matter, filters matter, medical capability matters. On Earth, many of these systems are hidden behind walls and utilities, and most people barely think about them. On the Moon, you would think about them every day because your life would depend on them every day, and the Moon does not usually kill you in one dramatic moment. That is another misunderstanding. It is more likely to kill you through a chain of ordinary failures: a bad seal, a clogged filter, a damaged suit, a failing pump, a weak battery at the wrong time. A maintenance mistake that would be minor on Earth and serious on the Moon. That is why the real challenge is not reaching the surface. The real challenge is making a hostile place act enough like Earth that a human body can continue functioning inside it. That is a very different goal, and it is much harder than a flag, a landing, or a short visit. That is the first shock. Getting to the Moon is a transportation problem. Staying there turns into a full-time survival problem. And once you accept that, the next question gets worse. Because even if your habitat works perfectly, your own body still has to live in 1/6 gravity. And that changes far more than people think. 1/6 gravity sounds like an advantage. In real life, it would start causing problems almost immediately. On the Moon, gravity is about 1.602 meters per second squared. That is roughly 1/6 of Earth's gravity. At first, that sounds great. You would weigh much less. You could jump higher. You could carry objects that look heavy much more easily. Your first impression might be that moving on the Moon would feel freeing, almost like your body suddenly got upgraded. That's only the first impression. The real problem is that low gravity does not give you more control. It gives you more airtime. That difference matters a lot. On Earth, when you walk, gravity helps keep your movement tight and predictable. You push off, your foot comes down, and your body settles quickly. On the Moon, the same push sends you higher and farther than your instincts expect. Apollo astronauts learned this very fast. Normal walking was awkward and inefficient, so they shifted into hopping and loping because that worked better in low gravity. That tells you something important. The Moon would not let you keep moving like an Earth human. Your body would start inventing a new way to move because the old one would stop making sense. And that sounds manageable until you remember something even more important. You would weigh less, but your mass would not change at all. That is where people get fooled. A battery pack, a drill, an oxygen tank, a toolbox, a crate of supplies, all of those things would weigh less on the Moon. So at first contact they would feel easier to handle, but the moment you try to push them, pull them, stop them, or turn them, mass starts telling the truth. The object still resists acceleration exactly the way it does on Earth. So a tool that feels light when you pick it up can still swing hard enough to wrench your shoulder. A large storage case can still slide with more force than you expect. A rover wheel can still trap a hand or pin a leg. Low gravity reduces load. It does not remove momentum. And in a place where every task already happens inside a suit with reduced dexterity and limited balance, that becomes a real safety problem very quickly. That changes work at a basic level. On Earth, your body has learned thousands of small corrections without you noticing. You brace automatically when lifting. You lean naturally when turning. You use friction, weight, and balance together without thinking. On the Moon, all of that would need retraining. Carrying equipment would be different. Loading vehicles would be different. Using power tools would be different. Even opening a stuck hatch or moving a container across the ground could become more dangerous, because the wrong amount of force could send you backward, twist your torso, or make both you and the object unstable at the same time. The moon would punish overcorrection just as fast as undercorrection. So maybe falling becomes less serious because gravity is weaker. That is true only up to a point, and that point arrives fast. Yes, on the moon you would fall more slowly than on Earth. That part is real. Lower gravity gives you less downward acceleration, so a stumble does not turn into the same kind of drop it would here. But the moon takes away other things that help protect you. There is no air to slow debris, no atmosphere to soften motion in any way, no soft ground in the Earth's sense. Lunar regolith is not fluffy soil. It is abrasive, sharp, and mechanically nasty. It has been broken down by impacts for billions of years, and without wind or water to smooth it, the grains stay jagged. So if you fall in a pressurized suit, you are not landing on something forgiving. You are landing on a surface that can scrape, damage, contaminate, and destabilize you. And the suit changes the risk again. A pressurized suit is not like protective clothing on Earth. It is bulky, stiff, and resistant to movement. That means if you start falling, recovering cleanly is harder. Your joints do not move as freely. Your center of mass feels different. Your hands are less precise. Getting back up can also be a serious task, not a quick reflex. Apollo astronauts dealt with this on short missions. In a permanent settlement where people would work outside more often and carry more equipment, falls would become a major operational concern. Reduced weight helps, but it does not cancel impact, awkward posture, equipment collision, or suit damage. The moon gives with one hand and takes back with the other. And then there is the bigger problem, the one we still do not have a clean answer to. What does 1/6 gravity do to a human body over months or years? We know a lot about two conditions. We know what 1G does because that is Earth. And we know a surprising amount about microgravity from space stations, where astronauts lose bone mineral density and muscle mass unless they follow aggressive exercise routines. But the moon sits in the middle at about 0.16 G, and that is a major scientific unknown. It might be enough gravity to preserve a lot of human health, it might be far too little. Right now, we do not know. That uncertainty is a serious problem for any long-term lunar plan. If bone loss continues there at a dangerous rate, then people might get weaker the longer they stay. If muscle loss remains severe, then routine work could become harder over time even with training. If the cardiovascular system adapts badly, then returning to Earth could become more difficult. If healing, balance, coordination, or inner ear function change in ways we do not yet understand, then the moon becomes not just a place to live, but a place where the human body itself is under test. A lunar base would not only be an engineering project, it would also be a long-running biological experiment happening in real time, with humans as the data. That has consequences beyond health charts and lab reports. It changes daily life, it changes design, it changes culture. Everything physical would need to be rethought. Climbing stairs would feel different enough that stair design itself might change. Carrying food, tools, water containers, or medical equipment would need new handling rules. Exercise would stop being optional and become part of survival planning. Construction methods would change because workers could move larger components more easily in one sense, but control them less safely in another. Rescue work would also be different. Pulling an injured person, stabilizing them, or moving them through an airlock would not follow Earth assumptions. Even something as simple as handing another person an object could go wrong more easily if both of you are less stable than you realize. And body language would change too. That sounds minor, but it is not. On Earth, a quick shove, a sharp turn, or a sudden grab usually happens inside a gravity system we know intuitively. On the moon, the same motion could destabilize both people much more easily. A frustrated movement during an argument could become physically dangerous. A rushed step on a ladder could become a fall. A missed footing on a platform could become an injury event that affects the whole crew. Low gravity would not just change athletics or heavy labor, it would change ordinary human interaction. That is the real point. On Earth, gravity is so constant that most people never think about it. On the moon, you would think about it every day because it would keep changing how safe, fast, and efficient every action can be. Walking changes, lifting changes, falling changes, Working changes, recovering from injury changes, even the way people stand near each other changes. Gravity stops being background physics and becomes one of the main forces shaping your life. And once your own body stops behaving the way Earth trained it to behave, the next problem gets worse. Because even if you learn how to move, the world outside still does not move through time the way your brain expects. On the moon, the cycle of day and night itself starts breaking your sense of normal life. You might think once you learn how to move on the moon, daily life starts to feel normal. It does not. The next thing that breaks is time. On Earth, your body gets constant help from the sky. Morning light tells you the day has started. Evening light tells you it is slowing down. Night tells your brain to wind down, sleep, recover, and reset. You do not usually notice how much your life depends on that cycle, because it has always been there. On the moon, that system stops working in the way humans are used to. A full lunar day, measured from one sunrise to the next, lasts about 29.5 Earth days. At most places on the moon, that means roughly 14 Earth days of daylight followed by about 14 Earth days of darkness. So there is no normal morning and no normal evening outside. There is no daily sunrise to anchor breakfast, work, exercise and sleep. There is no daily sunset telling your body it is time to stop. If you lived there, the outside world would stop being a clock. Your habitat would have to create one for you. That sounds like a small design issue until you think about what it really means. Sleep is not just a habit. It is biology. Hormones, alertness, appetite, mood, reaction time, memory, and judgment all depend on stable cycles. On Earth, light and darkness help regulate all of that without you doing much. On the moon, if you leave your body to follow the outside environment, your timing would become useless for normal human life. Nobody can organize a settlement around 2 weeks of day and 2 weeks of night as if that is ordinary. So the people living there would need artificial mornings, artificial evenings, artificial workdays, artificial sleep signals, and artificial routines. In other words, time would stop being something nature gives you and start becoming something your habitat manufactures. And that leads to another strange correction. You might assume that at least daylight would still feel familiar. It would not. Lunar noon would not look like Earth noon because the moon does not have a real atmosphere. On Earth, the sky looks blue because air scatters sunlight. That scattered light softens the world. It fills shadows. It creates twilight. It gives landscapes gradients and depth that your eyes and brain use constantly. On the moon, none of that exists. Even in full sunlight, the sky stays black. You could stand in bright daylight and still see a black sky overhead. That alone would feel wrong, but the bigger issue is what happens to contrast. Without atmospheric scattering, sunlight becomes harsh and direct. Bright areas are extremely bright. Shadowed areas can become almost completely black by comparison. There is no soft fade from light into shade, no cloud cover to soften glare, no haze to reduce extremes. If a rock, ridge, vehicle or crater wall casts a shadow, that shadow can become a serious visual problem immediately. You are dealing with sharp boundaries, strong glare, and sudden darkness. That matters for navigation, for EVA work, for landing operations, for construction, and for basic awareness of your surroundings. On Earth, your eyes get help from the atmosphere. On the moon, they get almost none. So even when the sun is up, the environment still does not feel open and normal. And then the landscape itself adds another layer to the problem. The moon is much smaller than Earth. Its radius is about 1,737 kilometers, compared with Earth's 6,371 kilometers. Because it is smaller, its surface curves away faster. That changes the horizon in a way people would notice more than they expect. For a person standing around 2 meters tall, the horizon on the moon is only about 2.6 kilometers away, roughly 1.6 miles. On Earth, for the same person, it is closer to 5 kilometers or around 3.1 miles. So even when you are outside in a huge open environment, the world starts dropping away sooner than your instincts expect. That can make the moon feel strangely closed in. It is airless, exposed, and enormous in one sense. But visually the landscape can feel cut short. You do not get the same long-distance openness that people unconsciously associate with being outdoors on Earth. The world bends away too quickly. Combine that with the lack of haze and the extreme lighting, and distance becomes harder to judge intuitively. Some features can seem closer than they really are. Others can disappear behind the curve earlier than you expect. So even your sense of space starts working differently. The moon is not just changing how you move, it is changing how far the world feels. And then there is Earth, which would not behave the way people expect either. If you live on the lunar near side, Earth does not rise and set like the moon does in Earth's sky. Because the moon is tidally locked to Earth, the same side of the moon always faces us. So from most places on the near side, Earth would stay in roughly the same part of the sky all the time, shifting only a little because of libration, which is a slight wobble in the moon's orientation. That means Earth would not feel like a passing object. It would feel fixed, constant, always present. That changes the emotional experience of the moon in a major way. Home would not be something that appears at night and disappears by morning. It would just be there, hanging above you, large enough to recognize as a world. Oceans, cloud systems, weather patterns, the colors of Earth, all of that would be visible from a place where none of it exists around you. For some people, that would probably feel grounding. For others, it would make homesickness much worse, because Earth would not be abstract, it would be visible and unreachable at the same time, and then the far side changes the whole picture again. On the lunar far side, Earth disappears completely. No blue world in the sky, no visual reminder of home, no constant symbol that civilization is nearby. Same moon, same gravity, same vacuum, but a very different psychological environment. On the near side, Earth is always there. On the far side, it is gone. That means different lunar regions would not only have different engineering conditions, they would have different emotional conditions too. So if the sky cannot guide your day, and even Earth behaves differently depending on where you live, how do you organize life at all? That is where the problem becomes bigger than individual comfort. It becomes social. A lunar settlement would need a fully artificial schedule. Sleep cycles, meal times, maintenance windows, shift changes, greenhouse lighting, power management, exercise routines, EVA planning, medical monitoring and psychological support would all need to run on indoor time, not outdoor time. In that sense, life on the moon would be like a submarine, Antarctica, and a spacecraft combined. You're cut off from a useful natural day, and the system around you has to keep your routine stable or your performance starts to break down. That raises a question most people never think about. Whose time would the moon use? UTC, Houston time, Beijing time, India time, mission elapsed time, a new lunar standard. That decision sounds administrative, but it would shape daily life. It would affect operations, international cooperation, communication windows, work shifts, and even identity. If people are ever born there, what would they say their day is based on? If different bases use different systems, how do you coordinate transport, emergencies, and shared infrastructure? On Earth, time zones feel normal because the planet rotates every 24 hours in a way humans can live with. On the moon, that natural system is too slow to use directly, so timekeeping itself becomes part of building a civilization. That is the deeper point. On Earth, time feels natural because the planet supports your biology without asking permission. On the moon, that support disappears. The outside world stops giving you a useful rhythm. Light becomes harsh instead of helpful. The horizon feels wrong. Earth hangs still or disappears completely depending on where you are, and your entire schedule has to be designed, enforced, and protected inside machines. So living on the moon would not just mean surviving in a hostile place. It would mean replacing one of the most basic human experiences, the daily rhythm of life, with an artificial system that never gets to fail. And once even time itself has to be engineered, the next question gets more dangerous. Because outside those walls, it is not just dark or bright. It is vacuum. And vacuum changes the basic rules of reality the second you step into it. You can adapt to low gravity. You can build a schedule. But the moment you step outside, the moon removes something even more basic than comfort. It removes the medium that makes normal life possible. Outside on the moon, there is almost no air at all. Technically, the moon has an exosphere, but for human survival, that does not help you. In practical terms, it is hard vacuum. There is no breathable oxygen, no usable pressure, and no atmospheric layer doing any protective work for your body. That changes the meaning of a simple action like going outside. On Earth, stepping outdoors means moving from one natural environment into another. On the moon, it means leaving the only place keeping your body alive and entering an environment where a failed seal can become fatal in seconds. That is not exaggeration. Human bodies are built for pressure. Your lungs need it, your circulation depends on it. The water inside your tissues and airways depends on it. A spacesuit is not just clothing. It is a personal pressure system, oxygen supply, cooling system, waste system, and survival shell all in one. If the suit fails, even in a small way, the problem becomes serious immediately. The same is true for a habitat. A wall is not just a wall. A hatch is not just a door. A valve is not just hardware. Every boundary between you and the lunar surface is holding back an environment that does not negotiate. That means outside is never casual. It is always a controlled exposure to a place that cannot support biology, even for a brief mistake. And once the air is gone, something else disappears with it that your brain depends on every day without you noticing. Sound changes completely. On Earth, sound travels through air. Voices, engines, footsteps, impacts, alarms, wind, distant traffic. All of that depends on a medium carrying pressure waves to your ears. On the moon, outside your suit, there is no real atmosphere to do that job. So if something moves nearby, it does not sound normal. A rover passing a short distance away would be silent unless vibrations reached you through the ground, your boots, your suit structure, or radio communication. A tool dropped on the surface would not make the kind of crisp sound your brain expects to hear in open space. An explosion in the distance would not roll across the landscape as a blast sound. You might see light, debris, or motion. You might feel vibration if it reaches connected material. But there is no air carrying a dramatic noise toward you. That would feel deeply unnatural because sound is part of how humans judge space, motion, and danger. Your brain uses sound to build awareness all the time. You hear a vehicle before you see it. You hear a problem in a machine before you open the panel. You hear a person approaching, a warning shouted, a crack, a hiss, a change in airflow. On the moon, many of those signals disappear the moment they are outside a pressurized volume. Reality gets stripped down. You stop experiencing the environment the way your senses were trained to experience it. That means operations depend even more on instruments, radio traffic, procedure, and visual awareness, because the world itself stops giving you normal sensory feedback. So if vacuum can already remove breath and even remove sound, what does that do to danger? It makes small failures much more serious than they look. A puncture in a spacesuit is not a clothing issue. It is a decompression emergency. A small leak in a habitat is not a maintenance annoyance. It is a countdown. On Earth, tiny failures are often tolerable for a while. A loose window seal is irritating. A small air leak in a building is inefficient. A minor gap around a door is something you fix later. On the moon, pressure loss is a life support problem from the first second it starts. The amount of time you have depends on the size of the leak and the volume affected, but the basic fact does not change. Pressure is your civilization. Lose it and everything turns into emergency procedure. And then there is the problem that sounds backward until you think it through. Fire could be more dangerous inside your habitat than many things outside it. Outside, the moon's vacuum does not support normal combustion. Without oxygen around a flame, fire cannot spread the way it does in air. Inside your habitat, the situation reverses. You have oxygen systems, electrical systems, plastics, fabrics, filters, electronics, batteries, wiring, and people trapped in a sealed space. That makes fire one of the worst kinds of internal emergencies. Smoke has nowhere useful to go. Toxic gases build up inside the same volume you need to breathe. You cannot just run outdoors because outdoors is lethal too. A fire inside a lunar habitat would force immediate decisions about isolation, suppression, atmosphere control, evacuation within compartments, and survival gear. On Earth, buildings are usually surrounded by survivable space. On the Moon, your building is the survivable space. And vacuum does more than create obvious emergencies. It also removes a huge list of quiet advantages that Earth's atmosphere gives you every day for free. There is no wind on the Moon, which means no natural cooling through convection. On Earth, heat leaves your skin and machinery partly because air carries it away. On the Moon, outside in vacuum, that does not happen. Heat management becomes harder and more technical. A machine in sunlight can absorb energy fast, and that heat does not simply blow away. The same problem affects suits, vehicles, tools, batteries, and habitats. Cooling has to be designed actively, not assumed. There is also no weather in the normal sense. No rain to clean surfaces. No wind to shift dust off equipment. No atmospheric drag to slow-moving objects. No air resistance to help with braking. A spacecraft cannot glide. It cannot flare like an airplane. It cannot use aerodynamic surfaces to save propellant. Exhaust plumes spread and interact with the ground differently. Dust clearing becomes harder because you cannot count on moving air to help you. Material surfaces exposed to vacuum can outgas, and in direct sunlight they can heat up fast. On Earth, the atmosphere constantly does invisible work for every machine, every building, and every person. On the Moon, every one of those services has to be replaced by engineering. That changes how you think about structures too, because vacuum turns every wall into a survival boundary. On Earth, a building mostly keeps out weather, noise, and temperature extremes. On the Moon, a building keeps in air, pressure, humidity, and the conditions required for human organs to keep working. That means architecture is no longer mainly about layout, style, or convenience. It becomes a pressure problem first. Pressure vessels, seals, hatches, valves, docking ports, suit joints, viewports, airlocks, all of them matter because each one is part of the line between life and a dead environment. The reliability standard changes. The inspection culture changes. Maintenance becomes more disciplined because the consequences are higher. Even trust changes. You're trusting that every technician, every manufacturer, every checklist, and every repair was done correctly. That is why living on the Moon would feel different at the most basic level. You would not just be living in rooms, you would be living inside systems that are continuously holding back vacuum. Every door closure matters, every seal matters, every pressure reading matters. Every strange sound inside a cabin matters precisely because outside there is no forgiving environment waiting to catch you. There is only exposure. So the vacuum changes everyday reality in a way that is easy to underestimate from Earth. It changes what outside means. It changes what silence means. It changes what a leak means. It changes what a fire means. It removes services the atmosphere used to provide without asking. And it turns every habitat into a machine that has to keep winning against the environment every minute of every day. And once air itself is gone, the next problem becomes even harder to manage, because vacuum does not just take away breath. It also makes heat behave in ways that can cook you in sunlight and freeze you in darkness. You might think vacuum is the most hostile part of the Moon. It is not the only one. Temperature would be fighting you all the time, and it would shape almost every decision a lunar settlement makes. On Earth, people treat temperature as a background condition. It changes, sometimes a lot, but the planet smooths things out. Air moves heat around, oceans store it, weather spreads it, buildings are designed inside a world that already moderates extremes for you. On the Moon, that moderation is gone. The surface can swing between conditions that are unbelievably hot and conditions that are unbelievably cold, and those extremes are severe enough to decide where you can work, where you can build, and whether your equipment keeps running at all. At the lunar equator, a sunlit surface can reach around 127 degrees Celsius, or about 260 degrees Fahrenheit. During the long lunar night, that same general region can plunge to roughly minus 173 degrees Celsius, or minus 280 degrees Fahrenheit. And the poles contain places that are colder still. In permanently shadowed craters, temperatures can drop below 100 Kelvin, and some measured areas have been near 40 Kelvin, which is around minus 233 degrees Celsius, or minus 387 degrees Fahrenheit. That is not just hot in the day and cold at night. That is an environment so thermally extreme that outside temperature stops being a weather report and starts becoming a survival boundary. That matters because humans do not live directly in those numbers, but everything keeping humans alive does. Suits do, batteries do, seals do, rovers do, solar panels do, pipes do, habitats do. If the wrong system sits in the wrong thermal condition for too long, it can fail even if nothing else is wrong. So temperature on the moon is not just something you endure, it is something you plan around constantly. And then there is the part that sounds helpful until you think it through. Sunlight is essential on the moon. It is also dangerous. With no meaningful atmosphere, sunlight arrives unfiltered at about the same solar intensity seen near Earth, roughly 1,361 watts per square meter at the top of the atmosphere scale. That is excellent for solar power. If you want energy, sunlight is one of your best options. But the same sunlight is brutal for exposed hardware. A surface in direct sunlight can heat up fast because there is nothing overhead diffusing or softening the incoming energy. At the same time, a surface in deep shadow can drop toward cryogenic conditions because there is no warm air around it and no atmospheric blanket holding heat in place. That means stepping from light into shadow on the moon is not a small visual change. It can be a major thermal change. On Earth, crossing into shade usually feels like relief. Under a tree or next to a building, the temperature difference is noticeable but manageable because the air still connects those spaces. On the moon, light and shadow are much more separated physically. A sunlit object can be heating rapidly, while a nearby shadowed area is cold enough to create a serious equipment problem. So light is not just visibility, it is thermal exposure. Shadow is not just darkness, it can be a cold trap, and that leads to a counterintuitive problem. Most people assume the cold is the main challenge. In many cases, getting rid of excess heat is even harder. On Earth, cooling happens in ways people barely notice. Air touches your skin and carries heat away. Fans help, wind helps, engines, electronics, and machinery shed heat into moving air. On the moon, in vacuum, convection is basically gone. Heat does not just blow away from a spacesuit, a rover, a computer rack, or an industrial machine. It mostly has to leave by radiation, which is slower, more limited, and much more dependent on surface design and exposure. That changes engineering at a deep level. A lunar spacesuit would not just need insulation to prevent freezing. It would need active systems to stop the astronaut from overheating. A habitat would not only need heaters for cold periods, it would need radiators and thermal loops to dump internal heat from people, electronics, lighting, batteries, pumps, and life support systems. The same is true for reactors, solar power systems, processing equipment, drills, and communications hardware. The problem is not simply staying warm. The problem is keeping every system inside its safe operating range when the outside world is trying to push it toward an extreme. So temperature control becomes constant. If a battery gets too cold, performance can collapse. If it gets too hot, lifespan can drop or failure risk can increase. If a seal cycles between extreme hot and extreme cold too often, material stress becomes a long-term durability issue. If a radiator is coated with dust or positioned badly, heat rejection suffers. The moon forces engineers to think thermally all the time because heat is no longer something the environment helps manage. It is something the environment actively complicates. So where do you build in a place like that? The answer may be the poles, not because they are easy, but because they are less punishing. The lunar poles are strategically valuable for a reason. Some elevated ridges near the poles receive sunlight for much of the year, which is extremely useful if you depend on solar power. Nearby, some deep craters remain in permanent darkness and can preserve water ice. That combination is almost too useful to ignore. You get access to long-duration sunlight for energy, relatively more stable thermal conditions than the equator, and nearby volatile resources that can support water supply, oxygen production, and maybe fuel production. That does not make the poles comfortable. They are still harsh, still cold, still dangerous, still nothing like Earth. But compared with 2-week days, 2-week nights, and severe equatorial heating, the poles start to look like premium real estate. Not because they are good, but because they are less impossible. That is an important distinction. Lunar settlement planning is not about finding ideal conditions. It is about finding conditions that reduce the number of impossible problems at the same time, and once you start thinking that way, temperature stops looking like a technical detail and starts looking like a force that will shape how lunar society organises itself. Work schedules would depend on thermal conditions. Travel routes might be safe only at certain sun angles or during certain parts of the local lighting cycle. Construction activity would have to consider how materials expand, contract, heat up and cool down over time. Some machines might need to shut down or hibernate during long dark periods if maintaining them is too energy expensive. Equipment storage would depend on how well you can protect hardware from thermal cycling. Farming systems would need stable indoor temperature control no matter what the outside environment is doing. Power planning would revolve around heat as much as electricity, because generating energy, storing energy, and using energy all create thermal consequences. Even industry might split by temperature. Some processes might benefit from permanent shadow because cooling is easier there. Others might cluster in near continuous sunlight because energy is easier to collect there. Certain landing zones might be preferred not only for terrain reasons, but because the thermal environment makes operations safer. Certain roads or rover paths might become standard because they avoid the worst heating or the worst cold traps. On Earth, cities often grow around water, trade routes and farmland. On the Moon, settlement patterns may grow around thermal logic, just as much as around resources. That is why temperature on the Moon would not feel like weather. Weather changes and passes. Lunar thermal conditions are structural. They decide what kind of habitat you build, what kind of power system you trust, where you store supplies, when you travel, and how much margin you have before routine operations become dangerous. If Earth gives you a climate and asks you to adapt, the Moon gives you thermal extremes and asks whether you can engineer around them every single day. And that makes the next problem even worse, because once you start building machines to survive vacuum and temperature, the Moon throws something else at all of them. It covers the entire surface with a material that gets into everything, damages everything, and follows you back inside. Lunar dust sounds like a minor problem until you look at what it actually is. It is not soft soil. It is not the kind of dirt you brush off and forget. On the Moon, the ground itself would behave like a long-term attack on your equipment, your habitat, and your body. The material covering the lunar surface is called regolith, and it formed over billions of years of impacts. Micrometeorites kept striking the surface and breaking rock apart again and again. But unlike on Earth, there was no wind and no flowing water to wear those particles down into smooth grains. So the fragments stayed sharp. Some are extremely fine, almost like powder. Others are more like abrasive grit. Many contain tiny glassy pieces created by impact heat. So when people casually say moon dust, that makes it sound harmless and familiar. It is neither. In practical terms, it is more like a mixture of crushed rock, fine abrasive and microscopic shards that had geological time to become a systems problem. That matters because on the Moon, the ground is not something you only touch with your boots. It gets onto suits, tools, rover wheels, airlocks, seals, cables, optical surfaces, and anything else that interacts with the outside environment. Every surface operation means contact with regolith, and every contact is a chance to carry that material somewhere you do not want it. This is not theory. Apollo already showed how quickly dust became a serious operational problem. Astronauts reported it sticking to their suits, scratching visor surfaces, degrading seals, and being dragged back inside the lunar module. Once inside the pressurized cabin, some described its smell as similar to burnt gunpowder. That detail matters because it reminds you this was not a distant engineering note buried in a report. It was immediate, physical, and hard to ignore. And those missions lasted only a matter of days. Even in that short time, dust became one of the most persistent annoyances crews had to deal with. That is the part people tend to underestimate. If dust caused real trouble during brief Apollo visits, then in a permanent settlement it would stop being a nuisance and become part of the core survival problem. The longer you stay, the more times you go outside. The more times you go outside, the more dust comes into contact with every moving part, every seal, every filter, every surface, and every procedure. A short mission can tolerate a headache. A long-term base cannot tolerate a headache that gets worse every week. And the moon makes this harder because the dust does not always behave like ordinary loose debris. It can cling in ways that are difficult to control. Part of the reason is electrostatic charging. Ultraviolet radiation from the sun and the solar wind can charge dust particles, which can make them stick to surfaces more aggressively than you would expect from simple gravity and contact alone. Near the terminator, the boundary between day and night, dust behaviour may become even more complicated. That means the regolith is not always just sitting there passively waiting to be stepped on. Under some conditions, it can become more mobile or more adhesive in ways that make basic cleaning much harder than it would be on Earth. So if you are designing for lunar life, you cannot assume a quick wipe down solves the problem. Dust can adhere to fabric, visor coatings, camera lenses, radiators, joints, seals, solar panels, and exposed mechanical interfaces. On Earth, a dirty surface is often an inconvenience. On the Moon, a dirty surface can mean worse thermal performance, reduced visibility, degraded mobility, or shortened component life. When a radiator collects dust, cooling can suffer. When a visor gets scratched, visibility drops. When a seal gets contaminated, pressure integrity becomes more uncertain. When a joint picks up abrasive particles, wear increases. Small contamination can turn into system degradation faster than people expect. And once you start thinking that way, the real risk becomes obvious. Dust is not only bad for machines, it is also bad for human lungs. You do not want this material inside moving mechanical systems, but you especially do not want it inside a habitat where people breathe. Scientists are still studying the exact toxicity profile of lunar dust exposure, but there are strong reasons to take it seriously. The particles can be very fine. They can have sharp edges. Freshly fractured surfaces can be chemically reactive. That combination raises concern for lung irritation and possibly long-term damage if inhaled repeatedly. On Earth, many dust hazards come from industry, pollution, or biology. On the Moon, the danger comes straight from geology. That creates a troubling situation. Lunar settlements would already rely on closed-air systems, filters, and repeated recirculation. If dust enters that system, then air quality becomes a much more sensitive issue. It is not only about comfort, it is about protecting respiratory health over months and years. Even if filtration is excellent, the settlement would still need strict procedures to prevent dust from coming inside in the first place, because once contamination enters the living volume, every cleanup becomes harder and every exposure becomes more meaningful. And that is why dust control would stop being a side issue and become one of the defining technologies of lunar civilization. A serious lunar base would likely need dust locks, soup ports, electrostatic cleaning systems, high-performance filtered air loops, specialized floor and wall materials, maintenance zones for contaminated gear, and strict protocols for movement between outside and inside. Soup ports may be especially important because they allow a suit to stay outside the habitat, reducing the amount of dust brought into living areas. Vehicles might need exteriors designed specifically to shed regolith, or at least isolate it from vulnerable systems. Habitats may need entry architectures built around contamination control as much as around pressure retention. Even clothing, storage, and cleaning routines would probably evolve differently from Earth because the environment keeps forcing the same lesson. If you let dust spread freely, the whole settlement pays for it. That would affect design language at every scale. Rovers would need protected joints and sealed bearings. Airlocks would need cleaning stages. Exterior tools might have dedicated handling systems to keep regolith away from sensitive interior zones. Surface walkways and floor materials might be chosen partly for how they manage tracked-in particles. Maintenance schedules would have to account for abrasion as a normal operating cost, not an unusual failure. In other words, dust would not just be something engineers solve once. It would be a constant tax on life, logistics, maintenance and safety. On Earth, dust is usually a housekeeping issue. You sweep it, filter it, wipe it away and move on. On the Moon, dust becomes several problems at once. It is a biohazard because you do not want it in your lungs. It is a wear mechanism because it grinds down moving parts. It is an optical contaminant because it degrades lenses, sensors and visors. It is a thermal problem because it can affect radiators and expose surfaces. It is a seal problem because it threatens the interfaces that keep air in and vacuum out. And because it is everywhere on the surface, you never fully get away from it. That is the deeper point. The Moon does not need storms, microbes or corrosive rain to damage a settlement. The ground itself is enough. Every EVA, every landing, every rover trip, every construction task, every sample movement, and every return through an airlock becomes another chance for regolith to spread through your systems. So a permanent lunar base would not just need life support and power, it would need a full contamination strategy built around the simple fact that the surface wants to come inside with you. And if ordinary dust can already threaten your machines, your seals, and your lungs, then the next danger is even more serious. Because outside the habitat, the Moon is not only abrasive, it is also exposed to radiation and constant micrometeorite strikes, which means every trip out the door becomes a timed risk. You can manage dust, you can manage temperature, but the moment you go outside on the Moon, another clock starts running over your head, and this one is counting radiation, particle impacts, and pure exposure. Earth protects you in ways most people never think about. The atmosphere above you absorbs or slows a huge amount of incoming radiation and burns up many small particles before they ever reach the ground. Earth's magnetic field also helps deflect charged particles from space. The Moon does not give you either of those protections in any comparable way. There is no thick atmosphere. There is no global magnetic shield doing the same job. So when you're on the lunar surface, especially outside a shielded habitat, you're exposed much more directly to the space environment. That includes galactic cosmic rays, which are high-energy particles coming from outside the solar system, and solar energetic particles, which can be blasted out by the sun during solar activity. It also includes secondary radiation created when those particles strike the lunar ground or the structures around you. In other words, the Moon does not just expose you to radiation from above. The interaction with the surface can make the environment around you more complicated too. Recent measurements from the lunar surface have put average radiation dose rates at around 1.3 millisieverts per day. Over a full year without serious shielding, that adds up to roughly 500 millisieverts. That is far above what most workers on Earth would normally be allowed to accumulate in a year. That number matters because radiation is not like a visible injury. You do not feel it happening in real time. You do not hear it. You do not smell it. You cannot rely on instinct to tell you when the risk is rising. It is cumulative, technical, and easy to underestimate if you are not tracking it carefully. So a lunar settlement would have to treat dose the way a submarine treats oxygen or a hospital treats infection control. It would be part of daily operations, not a side note for scientists. And then there is the more immediate version of the same problem. Cosmic rays are the steady background threat. Solar storms are the fast-moving one. A powerful solar particle event can drive radiation exposure sharply upward over the course of hours. That means a normal EVA can stop being normal very quickly if the space weather changes. On Earth, most people hear the phrase solar storm and think about satellite issues, GPS disruption, or maybe auroras. On the Moon, a solar storm could become a direct human safety problem. If you are outside when a major event develops, the mission changes immediately from surface work to shelter access. That means lunar operations would need reliable space weather forecasting in the same way coastal cities need hurricane forecasting. You would need constant monitoring, warning systems, predefined go or no-go thresholds, emergency recall procedures, and shelters with extra shielding ready to use fast. You would also need to think carefully about how far workers can travel from protected areas, because a warning only helps if people can get back in time. So astronomy, solar monitoring and survival planning start overlapping. On the Moon, watching the sun would not just be science, it would be operational safety. That changes how you think about distance too. A long rover trip would not only depend on oxygen, battery charge and terrain, it would depend on whether the crew could reach a shielded refuge if radiation conditions worsened. A base might need small hardened shelters distributed across work zones for exactly that reason. Not because daily life is impossible outside, but because outside is never truly stable. You're operating in a place where the sky itself can change the risk profile within a single work period, and radiation is only part of the outside problem. The moon also takes away another protection Earth gives you without asking. On Earth, many small space particles burn up high in the atmosphere before they can do damage. On the moon, they hit. Micrometeorites never get stopped by air because there is no atmosphere there to stop them. Even tiny particles can strike the surface directly, often at speeds between about 10 and 70 kilometers per second, or roughly 6 to 43 miles per second. That is far faster than any normal projectile people deal with on Earth. And when something that's small is moving that fast, size stops being reassuring. Tiny and hypervelocity is enough to matter. Most of these impacts are small and they are happening across the moon all the time. Over time, they chip away at exposed surfaces, damage equipment, degrade panels, and contribute to the constant grinding and fragmentation that creates and refreshes the regolith. That means micrometeorites are not only a sudden impact risk, they're also part of the long-term wear environment. A suit outer layer, a solar panel, a radiator, a window port, a rover surface, all of these things would be sitting in a place where fast particle impacts are part of reality. That does not mean astronauts would constantly be getting hit by dramatic visible strikes. The more serious point is that any exposed infrastructure has to be designed with that background hazard in mind. Over long durations, small repeated damage matters. A tiny puncture can matter. Surface pitting can matter. Gradual degradation can matter. And if the wrong impact hits the wrong weak point at the wrong time, the problem becomes immediate. So how do you reduce both the radiation risk and the micrometeorite risk? The answer is simple in principle and difficult in practice. You put mass between people and space. One of the best shields on the moon may be the moon itself. Regolith piled over a habitat by about 2 to 5 meters could provide meaningful protection, especially against solar particle events and part of the secondary radiation problem. That is one reason buried or partially buried habitats make so much sense for long-term settlement. They are not just efficient, they are protective. The same logic makes lava tubes especially interesting. If large lunar lava tubes are structurally usable, they may offer natural overhead shielding from radiation and micrometeorite impacts at the same time. That means the safest lunar home might not look open or futuristic at all. It might look buried, covered, recessed, or fully underground. Not because that seems dramatic, but because dose management and impact protection push design in that direction. On Earth, underground space is often optional. On the moon, it may become the preferred way to make long-term habitation medically and operationally safer. And once you accept that, the final point becomes unavoidable. Outdoor life on the moon would never be casual. You would not step outside the way people step into a backyard or take a walk. Every EVA would be a planned exposure period. Suit consumables would matter. Radiation forecasts would matter. Thermal conditions would matter. Communications would matter. Route planning would matter. Task duration would matter. Emergency return paths would matter. You would be checking how long the suit can support you, how far you are from shelter, what the sun is doing, what the terrain is doing, and what margin remains if anything changes unexpectedly. That means outside time becomes scheduled, measured, and limited. It is not open-ended, it is not casual, it is not a background setting for ordinary life. Even highly trained crews would be operating under layers of procedure because the environment leaves very little room for error. A walk becomes a mission. A repair becomes a mission. Collecting samples becomes a mission. Inspecting a rover becomes a mission. Opening the hatch starts a chain of constraints that stays active until everyone is back inside. That is the real change the moon forces on you. It turns the outdoors into a managed hazard zone. Radiation exposure has to be tracked. Solar activity has to be watched. Impact risk has to be accepted and engineered around. Distance from shelter has to be respected. The ground may look empty and still, but the danger is not gone. It is built into the environment itself, and that has a bigger consequence for settlement design than people first realise. Because if outside time is always limited, then the real centre of lunar life moves inward. It moves into protected structures, shielded corridors, sealed machines, and habitats that do much more than give you a place to sleep. They become the only environment where a human life can continue normally enough to feel like a life at all. You can survive limited time outside, but if your habitat fails, there is no second environment waiting for you. That is why a home on the moon would not really be a house in the normal sense. It would be a survival machine first, and a place to live second. On Earth, the world around your home already does most of the hard work for you. The atmosphere gives you pressure, the planet gives you gravity your body understands. Air spreads heat around. The environment blocks most small space debris, filters sunlight and supports breathing without asking anything from you. Your house mainly keeps out weather and gives you privacy, comfort and storage. On the moon, none of those background services exist outside the wall, so the habitat has to create them all from scratch and keep creating them every minute. That means the systems inside a lunar habitat would be doing far more than people normally associate with a home. Air handling would have to keep the right pressure and oxygen levels. CO2 scrubbing would have to keep exhaled carbon dioxide from building up. Humidity control would matter because too much moisture damages systems and too little dries people out. Thermal loops would have to move heat where it is needed and remove it where it becomes dangerous. Water purification would need to recover and clean water again and again because wasting it would be unacceptable. Fire suppression would have to work inside a sealed environment where smoke and toxic gases are a direct threat. Filtration would matter constantly because dust, particulates, microbes and trace chemicals all become more important in closed-air systems. And every major function would need redundancy because on the moon, a broken backup plan is not an inconvenience. It is a chain that can end with people dying. That changes the meaning of domestic life. You would not just live in rooms, you would live inside a system that is actively maintaining the conditions your organs need in order to keep functioning. The walls are not just structure, they are part of life support. The plumbing is not just convenience, it is recycling, hygiene, cooling and medical protection. The airflow is not just comfort, it is part of the chemistry of survival. That means a lunar home would never fully disappear into the background the way homes often do on Earth. People would always be aware, at least a little, that they are living inside a machine designed to imitate a planet. And once the habitat has to hold in pressure all the time, shape stops being an aesthetic choice and becomes a structural decision. Pressurized structures do not like arbitrary geometry. Pressure pushes outward in all directions, so certain shapes handle that stress much better than others. Cylinders, spheres, domes and other curved forms distribute loads more efficiently than boxy open rooms with lots of flat surfaces and large unsupported spans. That is why many serious lunar habitat concepts lean toward engineering first forms rather than anything resembling a suburban house or an apartment block from Earth. Inflatable modules, rigid cylinders, buried pressure vessels, and shells protected by regolith are all much more plausible than wide decorative layouts with lots of exposed corners and huge unsupported windows. This matters because the moon does not care what humans think looks cozy. It cares what can survive internal pressure, thermal cycling, dust exposure, and long-term structural stress. So architecture would shift. Interior design could still matter, maybe a lot for mental health, but the outer form would likely be driven by pressure efficiency, shielding, access, and repairability first. In other words, the outside of a lunar home may look more like infrastructure than like a dream house, because on the moon, infrastructure is what makes a home possible in the first place. That logic becomes even clearer when you get to the part of the habitat people would use every time that they leave or come back. The front door stops being simple. On Earth, a door mainly controls security, privacy, and weather. On the moon, the entry system becomes one of the most critical pieces of the entire settlement. Every trip outside risks losing air, bringing dust back in, contaminating seals and adding wear to parts that are already under stress. That is why airlocks would become central to daily life. And even more important, technologies like suit ports may become essential. A suit port allows the spacesuit to stay outside the habitat while the astronaut enters it from the rear through a docking interface. That means the dirty outer suit does not need to come fully inside the living space. At first glance, that sounds like a design detail. It is not. It could make the difference between a base that manages contamination and a base that slowly fills itself with abrasive dust and maintenance problems. The more often crews move in and out, the more important that difference becomes. So airlocks and suit ports would not just be technical systems, they would shape routine, architecture and culture. They would influence how people organise work shifts, where equipment is stored, how contamination is controlled, how fast crews can respond to emergencies and how much wear the habitat accumulates over time. On the Moon, your entry system would be one of the main places where survival and daily life meet directly. And that brings up another thing people always assume a home should have plenty of: windows. Humans like windows for good reasons. They reduce claustrophobia, they let in light, they connect interior life to the outside world. On Earth, windows are so normal that people rarely question them. On the Moon, every window becomes a trade-off. Transparent materials that can handle pressure differences, radiation, thermal stress, and micrometeorite risk are possible, but they are never free. Every opening in a pressure vessel is a structural and safety compromise that has to justify itself. That means lunar habitats probably would not have large panoramic windows everywhere just because people want them. More likely, visual connection to the outside would come through protected viewing ports, camera system, high-resolution displays, and perhaps a few carefully designed observation spaces with extra shielding. A true window on the Moon would not be decoration. It would be a controlled vulnerability that engineers allowed for a reason and protected heavily. The settlement might still create places where people can look out at the surface or at Earth, because that could matter a lot psychologically, but those places would be designed with the same seriousness as any other life-critical system. So even the experience of looking outside becomes engineered. The Moon keeps taking ordinary Earth features and turning them into decisions with structural, medical, and operational consequences. And then there is one more correction. People often talk about the Moon as if it is still and dead and therefore structurally simple. It is not that simple. Apollo seismometers showed that the Moon experiences moonquakes. Some are deep and tied to tidal forces, some are shallower. Some recorded events approached about magnitude 5. Because the Moon is dry, fractured, and very different internally from Earth, seismic energy can reverberate through it for surprisingly long times. On top of that, the surface and structures on it would also deal with thermal expansion and contraction across huge temperature swings. Materials heat, cool, expand, shrink, and accumulate stress over repeated cycles. That means even a buried or shielded habitat cannot be designed as if the ground underneath it is perfectly quiet forever. Foundations matter. Structural marges matter. Seals and joints have to survive not only pressure but also motion, vibration, and material fatigue. A lunar bunker would still need to respect local geology and long-term stress behaviour. The Moon may look static from a distance, but a permanent settlement would learn very quickly that dead-looking terrain can still create live engineering problems. That is the real picture. A lunar home would not be a retreat from the hostile environment. It would be the system standing between you and that environment all day and all night. It would make air breathable, water reusable, temperature survivable, pressure stable, dust manageable, and radiation somewhat less dangerous. Its shape would be chosen by stress. Its doors would be contamination control systems. Its windows would be limited and defended. Even the ground below it would have to be monitored and respected. Nothing about it would be casual, because nothing about life there could afford to be casual. And once your home becomes a machine that must keep winning against the environment, the next problem becomes obvious. Machines need supplies. People need air, water, and fuel. And if those things do not start coming from the Moon itself, then permanent settlement is not really permanent at all. A lunar base cannot live forever on shipments from Earth. The moment you ask for permanent settlement, the question stops being can humans survive there and becomes can the moon supply the basics of survival itself? For a long time that looked doubtful, especially when it came to water. The moon seemed dry in the way people feared most. Not dry like a desert with hidden reserves underground. Dry like a place that might force you to import one of the most important substances for life, hygiene, farming, cooling and fuel forever. That would have kept any settlement small, fragile and brutally expensive. But that picture changed when multiple missions started finding evidence that the moon is not as chemically empty as it once looked. Chandrayaan-1 helped identify signatures of water and hydroxyl on the moon. El-Taros deliberately impacted a permanently shadowed crater and detected water in the material thrown up by the collision. Orbiters such as the Lunar Reconnaissance Orbiter strengthen the case that ice exists in cold, permanently shadowed regions near the poles. That does not mean there are lakes waiting to be pumped. It does not mean you land, drill once and suddenly have easy access to clean water. The ice may be mixed with regolith, trapped in difficult terrain, unevenly distributed, and hard to extract economically. But the big point is much more important than the details. The moon may have the resource that decides whether it stays a temporary outpost or becomes something larger. Because on the moon, water is not just something you drink. That is the first Earth habit you have to drop. Water is life support, obviously. People need it to survive. But on the moon, it would also matter for hygiene, food production, cooling systems, industrial processes, and even radiation moderation in some shielded designs. Then there is the chemistry. Split water through electrolysis and you get hydrogen and oxygen. Oxygen supports breathing. Hydrogen and oxygen together can be used as rocket propellant. So the same kilogram of extracted water can support multiple critical systems at once. That makes water far more than a utility. It becomes one of the central strategic resources of the entire settlement. That changes the economics immediately. A base that gets water locally is not just reducing one resupply line, it is strengthening several systems at once. Local water can support people, crops, fuel production, thermal control and emergency reserves. Every kilogram you do not have to launch from Earth matters because launch mass is expensive, slow, and limiting. On Earth, water is so common people use it thoughtlessly. On the moon, every kilogram becomes part of a chain that touches survival, logistics, and expansion at the same time. And then there is an even stranger fact. The moon is not really poor in oxygen at the elemental level, it is poor in easy oxygen. A lot of lunar rock contains oxygen chemically bound inside minerals. By mass, lunar materials can be roughly 40 to 45% oxygen, but that oxygen is locked into oxides. It is part of the rock, not free gas waiting to be breathed. That means the moon is not oxygen poor in the way people casually assume. It is oxygen rich in a form that is difficult to use. To turn that oxygen into something a habitat can breathe, you need energy-intensive processing. That might involve chemical reduction, molten regolith electrolysis, or other industrial methods that take serious power and serious infrastructure. So the moon gives you the raw ingredient, but not the convenience. That is a repeating pattern there. The resources may exist, but they are almost always trapped inside engineering problems. You do not just find oxygen, you build a system that extracts it. You do not just collect water, you locate it, excavate it, process it, store it, protect it from loss, and route it into the rest of the settlement. That means permanent life on the moon would depend not only on natural resources, but on the industrial ability to unlock them reliably. And once you can do that, the whole meaning of the moon starts changing. Because then you are not only supporting life, you're creating propellant in a place where launching is much easier than it is on Earth. The moon's escape velocity is about 2.38 kilometers per second or 1.48 miles per second. Earth's is about 11.2 kilometers per second. That difference is huge. Getting material off Earth takes enormous energy because Earth is a deep gravity well. The moon is much shallower. So if you can produce fuel there, that fuel does not only support local rovers, landers, or backup systems. It can support traffic across cislunar space. It can support refueling depots. It can support spacecraft assembly and deep space missions that no longer have to haul every bit of propellant up from Earth's surface. That is when the moon stops being just a destination and starts looking like infrastructure. A lunar refinery could matter more than a symbolic landing ever did, because it changes the logic of transportation. If spacecraft can refuel with lunar-derived propellant, then the moon becomes useful not just for itself, but for everything operating between Earth and deeper space. Cargo movement changes. Mission design changes. Long-term exploration changes. Even commercial competition changes because control over resources and processing capacity starts to matter more than simple presence. In that sense, local fuel production could turn the moon into a transportation hub, not because life there becomes easy, but because gravity there is cheap compared with Earth. On Earth, launching heavy mass upward is one of the main cost drivers of spaceflight. On the moon, once the infrastructure exists, the same basic task can be done with much less energy. That one fact could reshape the entire map of inner solar system logistics. But even that is not enough by itself. Local extraction does not mean you can afford waste. In fact, it makes waste even more irrational. The International Space Station already recycles most of its water by recovering moisture, condensate, and even processed urine. It does that because resupply is expensive and limited. A lunar base would have to push that logic even further. If you worked hard to mine water, purify it, split some of it for oxygen and fuel and distribute it through a settlement, throwing large amounts away would be absurd. The same is true for air. Oxygen might be extracted locally, but losing cabin air carelessly would still mean losing processing effort, stored reserves and system margin. So recycling would not be an environmental slogan, it would be a hard operating rule. Closed-loop life support would need to recover water from breath, sweat, hygiene systems, waste streams and agriculture wherever practical. Air loops would need to minimize loss. Industrial systems would need to be designed to reduce waste at every stage. A growing settlement would not succeed by finding one resource once. It would succeed by using every critical resource again and again with as little loss as possible. That is the deeper reality of permanent life on the moon. Extraction matters, but extraction alone is not settlement. Settlement means integration. Ice mining has to connect to purification. Purification has to connect to life support. Life support has to connect to farming, cooling, shielding, and fuel chemistry. Fuel production has to connect to transport. Recycling has to connect to all of it. If any part of that chain stays weak, then the moon remains an expensive camp that depends on Earth for too much. If the chain starts working together, then the moon becomes something else entirely, a place that can support its own growth. That is why water, air, and fuel are not separate topics on the moon. They are one system. Water may keep people alive, produce oxygen, support crops, and make propellant. Oxygen may come from water or from rock. Fuel may come from the same chemistry that supports breathing. Recycling may connect every one of those flows into a tighter loop. Once that system becomes real, the moon stops being a place you visit and starts becoming a place that can sustain operations at scale. And that leads straight to the next hard limit. Even if you solve water, air, and fuel, people still need to eat. And food on the moon would not come from open fields, rain, or soil. It would come from agriculture trapped inside a pressure vessel, where every leaf is part of life support. You can mine water, extract oxygen, and make fuel, but none of that answers the most human question of all. What are you going to eat? And where does that food actually come from when there is no real outdoors to farm? This is where people often carry the wrong image from Earth. They picture greenhouses sitting on the moon the way farms sit in a cold desert or a dry valley here. But the moon is not a hard version of Earth. It is missing the entire background system agriculture normally depends on. There is no liquid water cycle moving through the environment. There is no breathable atmosphere. There is no living soil in the normal biological sense. There are no insects doing pollination. There is no open ecosystem quietly supporting plant life. So food production on the moon would not be farming a landscape. It would be running a controlled life support process inside sealed infrastructure. That means lunar agriculture would depend on hydroponics, aeroponics, algae systems, bioreactors, controlled environment agriculture, and carefully managed lighting, nutrients, humidity, airflow, and carbon dioxide levels. Every variable that Earth usually gives for free would have to be measured and controlled. Light would come from engineered systems or carefully filtered sunlight. Water would be delivered precisely and then recovered. Nutrients would have to be mixed, monitored, and recycled. Carbon dioxide from people might become an input for plants. Oxygen from plants could support the habitat in return. In other words, growing food on the moon would be much closer to running a laboratory than running a field. That changes the whole meaning of farming. On Earth, agriculture uses a planet. It uses weather, seasons, soils, rivers, microbes, and huge ecological support systems that took billions of years to develop. On the moon, agriculture uses pressure vessels, plumbing, power, chemistry, and system control. If one pump fails, one nutrient mix drifts, one fungal problem spreads, or one lighting schedule breaks, you are not just losing a crop. You may be damaging part of a larger survival loop. And that is why food stays tied to mass from the beginning. Until local production becomes reliable, every calorie is something you have to launch from Earth. Food is heavy, not just because of the edible material itself, but because of packaging, storage, spoilage protection, and transport constraints. Sending that mass across about 384,400 kilometers, or 238,855 miles, is costly every single time. A small early outpost could survive mostly on packaged food, just like orbiting stations do. That works when the crew is small and the mission is limited. But the moment you talk about a larger settlement, the math starts turning against you fast. More people means more calories, more variety, more storage, more waste, and more dependency on a supply chain that crosses cislunar space. That is why local food production would not be optional for long-term growth. Not because people want the romance of farming on another world, but because launch mass is unforgiving. Every kilogram of tomatoes, lettuce, herbs, grains, or protein you can produce locally is one less kilogram you have to launch out of Earth's gravity well. Every crop cycle that works reduces pressure on logistics. Every reliable harvest makes the settlement a little less fragile. On the moon, a fresh salad is not just food. It is proof that part of your life support burden has moved off the rocket manifest and into local infrastructure. And once you start growing plants, they stop being just food anyway. They start doing other jobs too. Plants can take in carbon dioxide and release oxygen. They can help regulate humidity inside a closed habitat. They can process parts of waste streams if the system is designed to use them that way. They can provide psychological relief in an environment full of metal, filters, seals, and machinery. That matters more than it might sound. A tray of green leaves inside a lunar habitat is not just a nutritional upgrade. It is also a biological subsystem and a mental health tool. That combination matters because lunar life would be mechanically intense. People would spend their days inside engineered spaces where almost everything is hard, measured, or procedural. In that setting, living plants could do something machines do not. They could make the habitat feel less sterile and less cut off from the kind of environment humans evolved in. Even a small growth chamber could change the emotional texture of a base. Fresh smells, moisture, green colour, visible growth. These things matter when most of your world is pressure walls and equipment racks. So farming on the moon may end up teaching a lesson that sounds simple but becomes much bigger in practice. Food production is not just an economic sector. Away from Earth, it becomes part of what makes life psychologically sustainable. But that does not mean you can just plant crops in lunar dirt and move on. That is another shortcut that fails the moment you look closely. Lunar regolith is not ready-made potting soil. Yes, scientists have tested plant growth in lunar soil simulants and in very limited cases with Apollo material under controlled conditions. Those experiments are useful, but they do not mean raw moon dust is a practical agricultural medium. Regolith has sharp particles, poor structure, almost no organic content, no established soil ecosystem, and possible chemical reactivity issues that could complicate root health and nutrient management. It is not the kind of material you would casually fill a planter box with and trust for long-term food production. So realistic lunar agriculture would probably rely on processed growth media, imported additives, heavily treated substrates, or fully soil-free systems like hydroponics and aeroponics. Those approaches give you much tighter control over water, nutrients, cleanliness, and plant response. They also fit better into a settlement where efficiency matters more than tradition. On Earth, people can afford to work with messy biological complexity because the planet is full of it. On the Moon, this bias will be toward control. You're not sticking seeds in moon dust and calling that a farm. You're building a precise agricultural system that happens to operate off Earth. And once food production becomes technical, diet starts changing too, not just in a nutritional sense, but in a cultural one. Fresh produce would be valuable because it is hard to grow, and valuable for morale. Water-intensive foods would stay expensive. Animal agriculture, especially early on, would be extremely inefficient because feeding animals, managing waste, and supporting their life systems would cost too much compared with the calories returned. That means lunar diets would likely lean toward crops that produce a lot with relatively little water, space, and energy. Leafy greens, compact vegetables, nutrient-dense plants, microbial proteins, algae-based foods, fermentation systems, and eventually cultured foods could all become part of the mix. That would change cuisine. It would change celebration. It would change what counts as luxury. On Earth, people often treat food variety as ordinary. On the Moon, variety would be planned, earned, and rationed through biology and engineering. A fresh strawberry might feel special in a way people on Earth barely understand. A holiday meal might depend on months of growing cycles and careful storage. Protein could come less from livestock and more from bioreactors or cultured systems. Menus might be built around efficiency first and tradition second, especially early on. And food culture would still matter because humans do not just eat for fuel. They eat for routine, comfort, identity, and social life. That means lunar settlements would eventually need more than calorie paste and vitamin charts. They would need meals people actually want, foods tied to home cultures, and systems flexible enough to support morale as well as survival. But every choice would still sit inside hard constraints of mass, water, energy, and space. On the Moon, dinner becomes logistics, chemistry, and identity all at once. That is the real picture. Food on the Moon would not come from open land, normal soil, or natural seasons. It would come from sealed systems that are part farm, part lab, part life support infrastructure. Every crop would be tied to power, water recovery, nutrient control, air chemistry, and human psychology. Every harvest would reduce dependence on Earth a little more, and every failure would remind the settlement that eating off-world is not a background activity. It is one of the hardest technologies you have to maintain. And even if you solve food, the next limit is still waiting outside the habitat wall. Because people do not only need to eat, they need to move, work, travel, build, and cover distance. And on the Moon, getting from one place to another would be slower, rougher, and much more engineered than most people expect. Growing food solves one problem, it does not solve movement. A lunar settlement can have air, water, fuel, and crops, and still stay trapped if it cannot move people and cargo across the surface safely and efficiently. That is where another common assumption breaks down. People hear the phrase moonwalk and think of something graceful, slow, almost relaxing. In real life, walking outside on the Moon would always be operational. It would never be casual. A spacesuit is not clothing. It is a pressurized machine wrapped around your body. It protects you, but it also fights you. The joints resist motion. The gloves reduce finger strength and fine control. The backpack adds bulk and life support limits. The whole system uses energy and creates fatigue. Apollo astronauts proved that surface movement is possible, but even short trips were physically demanding. Tasks that look simple on paper become harder when your hands are thick, your range of motion is limited, and the ground under you is dusty, uneven, and unfamiliar. On the Moon, walking is work. Every step consumes attention, effort, and system margin. That changes how you think about distance immediately. On Earth, if something is a kilometre away about 0.6 miles, a healthy person can usually just walk there without turning it into a mission. On the Moon, that same distance outside in a suit becomes part of an operational plan. You're not just asking how far it is, you're asking how much oxygen it uses, how much battery it uses, how much fatigue it creates, how much dust exposure it adds, and how fast you can get back if something goes wrong. That means movement on foot stays limited even if gravity is lower. Gravity helps with weight. It does not erase suit fatigue, terrain risk, or time pressure. And once walking stays expensive, vehicles stop being optional support equipment. They become part of the settlement itself. Rovers on the Moon would not just be transport. They would be mobile life support platforms, workstations, cargo haulers, communication relays, and emergency shelters. A small unpressurized rover or cart could help with short-range movement, tool transport, and basic field operations. But a pressurized rover changes the map much more seriously. With one of those, people can travel farther without staying in suits the whole time. They can carry more equipment, extend work time, and still keep some protection from vacuum, dust, and radiation. That turns the Moon from a tiny circle around one habitat into a much larger operating region. That difference matters more than it first sounds. A base without effective rover systems remains a small island of survival. A base with reliable long-range mobility starts becoming a territory. You can reach polar resources, you can inspect infrastructure over wider areas, you can build distributed systems instead of packing everything into one vulnerable point. You can recover equipment from farther away. You can support science, mining, construction, rescue and maintenance at larger scale. In that sense, the difference between a science outpost and a real settlement may come down to rover range more than people expect. But even with good vehicles, the Moon creates another problem that is easy to underestimate. Distance itself is visually deceptive there. Apollo astronauts reported that with no atmosphere to create haze, far objects could look closer than they really were. On Earth, your eyes and brain use atmospheric scattering as one of many distance cues. Far hills look softer. Distant objects lose contrast. The air itself helps your brain estimate scale. On the Moon, that cue is mostly gone. A ridge, boulder, or crater edge may look surprisingly near when it is not. Combine that with the shorter horizon, harsh lighting, deep shadows, and unfamiliar terrain, and your natural depth intuition becomes less trustworthy. That matters because navigation errors on the Moon are not small mistakes. If a crew misjudges distance, they may burn more time, energy, and consumables than planned. If a vehicle operator misreads terrain, the route may become slower or more dangerous. If someone thinks a shelter or habitat is closer than it really is, that error can grow into a serious emergency. So lunar travel would depend heavily on instrumentation, mapped routes, beacons, local navigation systems, and strict procedures. You would not trust your eyes the way you do on Earth. You would verify with data. The Moon punishes casual judgment, especially when casual judgment feels correct. That starts shaping infrastructure too, because movement is not only about legs and wheels, it is also about what kind of surface you're moving across and what keeps damaging that surface every time a spacecraft arrives. Landing on the Moon throws up one of the nastiest engineering problems on the surface. Rocket exhaust can blast loose regolith outward at high speed, turning the landing zone into a debris source. That means every arrival can sandblast nearby equipment, chip exposed surfaces, contaminate systems, and damage hardware that was working fine seconds earlier. A permanent settlement cannot tolerate that for long. If every ship arrival attacks the base with high-speed dust and fragments, then traffic itself becomes destructive. So infrastructure would probably begin with practical protections, not with grand architecture. Hardened landing pads would become important early. Berms or barriers to redirect debris would matter. Prepared routes between key areas would matter. Surface stabilization could become one of the first major construction priorities. That might mean sintering regolith with heat, melting the top layer into a more solid surface, laying down prefabricated mats, or using other methods to stop loose dust from becoming a hazard every time engines fire. The same logic applies to roads. On Earth, roads are mostly about speed, convenience, and weather resistance. On the Moon, roads may start as damage control systems. They help vehicles move more predictably, reduce dust disturbance, support logistics, and protect critical equipment by organising where traffic goes. Before the Moon gets anything that looks like normal urban development, it may have to solve a more basic problem first: how to move ships, rovers, and cargo around without eroding its own operating environment every day. And then the story flips in an unexpected direction. Because although getting around on the surface is difficult, leaving the Moon is much easier than leaving Earth, and that changes the long-term meaning of lunar transportation completely. The Moon's gravity is low enough that launching cargo or vehicles from its surface takes much less energy than launching from Earth. Earth's escape velocity is about 11.2 kilometers per second, or around 7 miles per second. The Moon's is about 2.38 kilometers per second, roughly 1.48 miles per second. That difference is enormous. It means the Moon is a much shallower gravity well. Once you have the right infrastructure there, moving mass off the Moon becomes much more practical than moving the same mass off Earth. That opens doors that sound unrealistic now, but become logical if a real lunar industrial base appears. Reusable landers make more sense. Fuel depots become more valuable. Cargo launch systems designed for lunar conditions become more plausible. Some people even study concepts like electromagnetic launch systems or cargo catapults for moving material into lunar orbit. Those ideas are extremely hard, but compared with doing the same job from Earth, they stop sounding absurd. The physics are simply more favourable. That is where transportation stops being only a survival problem and starts becoming a strategic advantage. At first, mobility is about getting workers to a crater, getting supplies back to the habitat, and making sure nobody dies because a rover failed too far from shelter. But later, the same transportation network could support mining, manufacturing, orbital construction, fuel export, and deep space missions. A place that begins as a harsh outpost can start turning into a logistics platform for the wider solar system. That is a huge shift. In the early phase, transportation on the Moon is restrictive, tiring, procedural, and dangerous. Walking is slow, suit work is exhausting, terrain is deceptive, roads are unfinished, landing is disruptive. But if the settlement survives long enough to build real mobility systems, those same constraints can start producing an advantage. The Moon is hard to live on, but it is easier to launch from. That means a civilization that learns how to move efficiently there may gain a major position in space infrastructure. So getting around on the Moon would not feel like freedom at first. It would feel controlled, limited, and expensive. Every trip outside would be measured. Every kilometre would have a cost. Every rover would be part vehicle and part survival machine. Every route would depend on engineering, mapping, and discipline. But over time, transportation is also where the Moon could become more than a place to endure. It is where a settlement could begin turning its hostile environment into leverage. And that creates the next problem. Because even if the machines work and the roads improve, the biggest uncertainty is still the human body itself. The hardware might adapt to the Moon before biology does. A lunar settlement can solve power, water, food, and transport, and still hit the hardest limit of all. The human body may not adapt the way people hope it will. That is what makes the Moon different from a normal frontier story. A lot of the engineering problems look brutal but understandable. You can build shielding, you can build habitats, you can recycle water, you can mine ice. But biology is slower, less predictable, and much less willing to follow a plan. The moment people stop visiting the Moon for short missions and start living there for months or years, the question changes. It is no longer just can humans survive there. It becomes what kind of human life can actually continue there without breaking down. Start with bone and muscle, because this is one of the clearest warning signs from spaceflight. In microgravity, astronauts lose bone density and muscle mass unless they fight it with intense exercise. That is already a major issue in orbit. Lunar gravity is not zero, but it is only about 0.16 g. That might help. it might slow the losses, but nobody knows by how much over long periods, because humans have never lived for months or years in 1/6 gravity. That is a huge gap in knowledge. And this is not just about fitness, it is about whether daily life remains physically sustainable. If bone keeps thinning, fracture risk rises. If muscle weakens too much, work becomes harder, recovery becomes slower, and returning to Earth becomes more difficult. If partial gravity turns out to be not enough to preserve healthy function over long periods, then a lunar settlement has a built-in biological limit no matter how good its engineering is. Exercise systems would help, but they may not solve everything. The real test is not whether a person can survive a mission, it is whether people can work, heal, age, and maintain full physical lives there over time. And once you think past the first generation of settlers, the uncertainty gets much bigger. Can people develop normally in 0.16 G? Can people grow old there without major damage? Can injuries heal the same way? Can the body handle development in that environment? Right now, those are not answered questions. A permanent settlement is not truly permanent until humans prove that whole life cycles can happen there, not just short-term stays by highly trained adults. Then the radiation problem changes the health discussion again, because on the Moon, staying alive is only part of the medical picture. Lifetime risk starts moving into the centre. Chronic exposure to space radiation raises concern about cancer, cataracts, nervous system effects, and cardiovascular damage. Shielding reduces that risk, and buried habitats would matter a lot, but no lunar resident gets to forget the dose budget. Every EVA adds exposure. Every year on the surface adds exposure. Every design decision about shielding, work schedules, and where people sleep becomes part of a medical strategy measured not only in comfort, but in long-term disease risk. That is a strange reality compared with the Earth. On Earth, your home does not quietly add to your future cancer risk unless something is badly wrong. On the Moon, your habitat design, wall thickness, location, and work routine all feed into that calculation. Doctors would not only be asking whether a person can do a job today, they would also be asking how much dose that person has already accumulated this year, over 5 years, over a career. Medical planning would become deeply tied to architecture and operations, and radiation is only one part of the everyday health burden. The closed environment itself would start creating its own medical pattern. Even with excellent filtration, a lunar habitat would still have to manage dry air, trace contaminants, particulates, off-gassing from materials, and the normal microbial problems that appear when people live together in sealed spaces for long periods. Add abrasive dust that can enter at low levels despite strict controls, add fatigue from suit work, add altered exercise demands, and you get a medical environment that does not match anything most people experience on Earth. That means doctors on the Moon might spend a lot of time dealing with problems that look ordinary at first but behave differently there. Irritated eyes, skin dryness, respiratory irritation, joint strain from suit use, repetitive stress injuries from tools and gloves, contamination issues from dust, sleep-related performance decline, minor wounds that become more complicated because the environment is tightly controlled and evacuation is slow. Over time, the Moon may force the creation of a new kind of occupational medicine built around sealed habitats, partial gravity, abrasive dust, radiation tracking, and constant equipment interaction. And then the worst question arrives. What happens when something serious goes wrong and the patient cannot just be transferred to a hospital? A burst appendix on Earth is dangerous, but usually survivable because the system behind the patient is large and fast. There are surgeons, imaging machines, blood supplies, anesthesiologists, specialists, sterile facilities, backup teams, ambulances, helicopters, intensive care units. On the Moon, the same emergency becomes a much more serious test. A severe injury, decompression accident, internal bleeding, infection, cardiac event, or complicated fracture is not just a medical case. It is a logistics problem, a staffing problem, an equipment problem, and possibly a transport problem lasting days. That means a lunar clinic could not be a small first aid room with a few advanced tools. it would need far more autonomy than most expedition medicine has ever required. You would need imaging capability, surgical equipment, robust pharmacy stocks, procedures for partial gravity care, ways to handle trauma, and crew trained well beyond ordinary field medicine. Some settlement members might need to be full-time medical specialists, not just astronauts with cross-training. And even then, the reality would stay hard. Some conditions that are manageable on Earth would become much more dangerous simply because you are far from the depth of care modern medicine usually depends on. That alone makes lunar life medically intense. But the biggest unanswered issue is still ahead, and it is the one that decides whether the moon ever becomes a real society instead of a rotating adult outpost. We do not know how vestibular systems would develop in people who never grew up under 1G. We do not know how organ development, immune programming, or hormonal systems would behave across a whole generation in lunar conditions. That is where the stakes rise the most. A base is one thing, a society is something else entirely. Adults can endure a lot in controlled missions. A society has to support development from the beginning of life. It has to support healthy aging, recovery, and generational continuity. If lunar gravity turns out to be enough, then the moon becomes much more viable as a long-term human world. If it is not enough, then permanent settlement may always depend on limits, rotations, or artificial gravity solutions that do not exist yet at scale. And that means the biggest unknown on the moon is not hidden in the ground or the sky. It is inside the people living there. We know the moon can challenge the human body. We do not yet know whether it can support a full human future. Bone, muscle, radiation burden, respiratory health, emergency medicine, all of these are still part of one unfinished experiment. So the moon would not only test machines, it would test what kind of animal a human being really is. Can you remain healthy in 1/6 gravity for years? Can you recover there? Can a community become self-sustaining there, not just mechanically, but biologically? Until those questions are answered, every serious lunar settlement plan carries a quiet warning inside it. The hardware may work before the body does, and even if the body holds together, there is still another limit people underestimate. Because a lunar settlement would not only be hard on bones, lungs, radiation budgets, it would also be hard on the mind. And for many people, that may become the toughest part of all. You can solve air, water, food, radiation shielding, and medicine, and the moon can still break you in a different way. The hardest failure might not happen in the hardware, it might happen in your head. That sounds strange at first because space is usually framed as a technical problem. Build the right suit, build the right habitat, build the right power system. But people do not live by engineering alone. People live by routine, privacy, sensory comfort, social space, and the quiet feeling that the world around them makes sense. On the moon, a lot of that disappears or gets distorted, and that matters more than people usually admit. Start with the distance from Earth, because the moon creates a very specific kind of loneliness. Mars is so far away that the separation is obvious. Nobody going to Mars expects Earth to feel close. The moon is different. It is close enough to stay emotionally present. You can talk to people with only a brief delay. On the near side, you can actually see Earth in the sky. You would know the oceans are there, the weather is there, the cities are there, the air is there, normal life is there. In cosmic terms, home is right next door. In practical terms, it is completely unavailable whenever you need it most. That can make homesickness worse, not easier. Distance is easier to process when it is absolute. The moon gives you a version of closeness that keeps reminding you what you cannot reach. You can hear people back home. You can see the planet they're standing on. But you cannot step outside and feel wind. You cannot go for a drive. You cannot walk in a park. You cannot stand in the rain. You are close enough for Earth to stay real every day, and far enough that Earth cannot comfort you physically. That is a hard psychological position to live in for months or years. And then there is the fact that early lunar life would almost certainly be crowded in the wrong ways and cramped in the wrong ways. Privacy would be limited, and that changes human behaviour fast. Early habitats will not be spacious. They will be compact because mass is extensive, pressure vessels are expensive, and every cubic meter has to justify itself. That means noise carries, schedules overlap, small habits become visible, small annoyances build up. On Earth, when people get irritated, they often cool off by changing environments. They leave the room, they go outside, they drive somewhere, they take a walk, they get physical distance from the conflict. On the Moon, that is much harder. Going outside is not casual. It is procedural, costly and limited. So the ordinary human pressure release valves get weaker. That means crew selection is not just about skill, it is about compatibility under stress. Social design is not a luxury. Recreation is not a side activity. Conflict resolution is not soft science. All of that becomes part of the survival system. A crew that stops functioning well together can damage decision-making, maintenance discipline, and emergency performance. On the Moon, a bad social environment is not just unpleasant. It can become a safety hazard. That is why psychology would be infrastructure. The settlement would need routines, private zones, communication norms, entertainment, emotional support, and ways to absorb friction before it starts affecting operations. And even if the crew gets along, the environment itself would keep taking away things the human mind uses to stay balanced. The Moon gives you almost no natural sensory relief. No wind, no rain, no trees moving, no birds, no ocean noise, no smell of wet soil, no changing seasons in the way people know them on Earth, no casual wandering outside without preparation. Even the sky does not behave the way your brain expects. It stays black in daylight. Shadows are too harsh, the horizon feels wrong. The environment is visually striking, but it is not rich in the kind of sensory variation human beings evolved around. That matters because people are not built for sterile repetition without cost. If your whole life becomes metal walls, recycled air, controlled lighting, machinery noise, scheduled work, and occasional high-risk trips outside, the mind can start flattening things out. Days begin to blend together. Motivation can fade, small problems can feel bigger because there is less sensory reset built into life. A lunar habitat that ignores this could become mentally exhausting even if it is physically safe. So beauty may have to be engineered on purpose, not as decoration but as mental support system. Lighting design would matter, colour would matter, sound design would matter, visual access to plants would matter, communal spaces would matter, maybe simulated skylight would matter, maybe protected observation room with views of Earth would matter. The Moon may force humans to take emotional architecture more seriously than ever before, because the environment outside is not going to help. And then the time problem returns in a more personal way. The Moon does not support normal human rhythms, so mental health would have to fight for stability all the time. The outside day is too long to guide sleep or work. So people would live by artificial lighting cycles, artificial schedules, artificial mornings, and artificial nights. That already creates risk. Add long mission duration, limited social variety, sealed environments, and high responsibility, and you get conditions that are known to disrupt sleep, mood, and performance. Antarctica teaches us part of that. Submarines teach us part of that. Space stations teach us part of that. The Moon combines pieces of all of them while adding vacuum outside every wall and a much harsher sense of isolation. Poor sleep is not just tiredness. It affects memory, focus, judgment, emotional control, and team dynamics. Depression does not stay personal in a place where everybody depends on everybody else. Anxiety does not stay abstract when every system around you matters. Cognitive fatigue can turn into operational mistakes. Social strain can turn into poor decisions. So mental health on the Moon would not be handled as a private issue you talk about later. It would need active monitoring, structured routine, built-in support, and a culture that takes it seriously before it starts damaging the mission. And through all of that, Earth itself may become one of the strangest psychological tools the Moon offers. On the near side, Earth would stay visible in the sky, and that could matter a lot. For some people, it may act like an anchor, a reminder that home still exists, a stable visual connection to everything familiar. Something to look at when the habitat feels closed and the mission feels heavy. But for other people, that same sight may intensify the problem. It may sharpen longing instead of easing it. It may make the distance feel more personal. Either way, Earth would not be emotionally neutral. It would have psychological weight. That is why life on the moon would test something deeper than engineering competence. It would test whether humans can build a meaningful emotional life away from the biosphere that shaped every instinct we have. Can people feel normal without open air? Can they stay mentally strong in sealed structures with artificial time and limited privacy? Can they keep relationships stable under constant operational pressure? Can they create joy, routine, intimacy, and identity in a place that strips away so many of the natural things Earth gives for free? That may be the hardest question of all, because a machine can survive without beauty, privacy, weather, or touch with nature. A human being cannot do that forever without paying some price. The moon will not only ask whether we can stay alive there, it will ask what kind of life still feels worth living once you are there. And if the psychological pressure is already that high during the normal operations, then the final question gets sharper. Because when something actually goes wrong on the moon, there is no dramatic speech, no heroic delay, and no extra time. Emergencies become brutally simple. Fix it, contain it, or die. The moon does not give you much room for mistakes, and that changes what an emergency means. On Earth, many failures begin as problems and only later become disasters. On the moon, some failures begin as disasters immediately. The clearest example is decompression. A suit puncture, a hatch failure, gear, a bad valve, a cracked line, or a structural breach is not something you calmly schedule for later repair. The moment pressure starts dropping, time becomes the main factor. Human bodies are built for a narrow pressure range, and the systems around you are built to protect that range. If the boundary fails, the problem is no longer abstract, it becomes physical right away. That is why lunar survival would depend so heavily on redundancy, compartmentalization, pressure sensors, leak detection, drills and checklists. You do not wait and see, you isolate, seal, patch, repressurize or get inside a safe volume immediately. That would shape behavior at every level. A suit inspection would not be routine in the casual sense. It would be one of the last lines between a worker and vacuum. Hatch discipline would matter. Seal cleanliness would matter. Pressure readings would matter. Training would matter, because in a real decompression event, people do not have time to debate. They have to know what to do and do it fast. The moon is too unforgiving for heroic improvisation to be a plan. If your crew depends on last-minute brilliance more than on procedure, then your system is already weaker than it should be. And decompression is only one kind of emergency. The one people often underestimate is fire, because on Earth fire is familiar enough that people think they understand it. A fire inside a lunar habitat would be much worse than many threats outside. Outside, the moon's vacuum and lack of oxygen stop normal combustion from behaving the way it does on Earth. Inside the habitat, the logic reverses. Inside is where the oxygen is. Inside is where the wiring is, the batteries, the electronics, the plastics, the filters, the storage compartments, the fabrics, the people, the sealed volume, and the limited escape options. If a fire starts there, you are not in an ordinary building. You're in a pressure vessel full of life support systems that can be damaged by heat, smoke, and toxic byproducts. That means fire response on the moon would need to be extremely serious. Smoke control is not optional. Compartment isolation is not optional. Emergency breathing gear is not optional. Atmosphere management is not optional. People may need to seal sections off fast, cut power to affected zones, suppress flames without damaging the rest of the habitat, and protect the breathable environment for everyone else at the same time. On Earth, if a kitchen fire gets out of hand, people can often run outside and wait for help. On the moon, outside is not a refuge. Outside is another lethal environment. So a fire can trap you between two bad options very quickly. That is why an internal fire could be more frightening than a moonquake. It attacks the only habitable space you have, then there is power loss, which sounds ordinary until you remember what power is actually doing on the moon. It is running the life support, the air handling, the pumps, the filters, the communications, the computing, the medical systems, the thermal management, the water recycling, and much of the settlement's ability to function at all. On Earth, a blackout is often disruptive and expensive. On the moon, power failure can turn into a survival crisis. The timing of that failure matters. Lose power in a sunlit period and you may still have a chance to stabilise the situation with solar input, stored reserves, and reduced loads. Lose it deep into a 14-day lunar night without enough backup capacity, and the whole settlement enters a much harder fight. Heat has to be maintained. Batteries have to last. Critical systems have to be prioritised. Some sections may have to be shut down to protect others. A short outage can begin a chain reaction if the settlement is not designed to fail gracefully. That is why lunar bases would need layered power architecture, not just one good source. Batteries matter. Fuel cells matter. Maybe nuclear systems matter. Load shedding protocols matter. Emergency thermal survival modes matter. The settlement would need to know exactly what can be shut off, for how long, and in what order without causing damage that makes recovery impossible. On Earth, people often talk about resilience as a nice property to have. On the moon, resilience in the power system is part of the difference between a recoverable problem and a dead habitat. And even when all of that is understood, one fact stays brutal. Rescue from Earth is real in principle, but useless on the timescale many emergencies actually care about. A rescue vehicle is not a helicopter waiting on the next pad. Even under good conditions, a mission from Earth needs launch preparation, departure, transit, lunar arrival, and landing. That takes time, a lot of time compared with what the human body wants during trauma, decompression, infection, internal bleeding, respiratory crisis, or major system failure. So the moon forces a very uncomfortable truth on any settlement plan. You have to be ready to solve most serious problems locally, because Earth cannot arrive fast enough to save you from the worst ones. That changes the philosophy of operations. Backup cannot be external first, it has to be local first. The medical systems have to be deeper, spare parts have to be broader, emergency stores have to be real, not symbolic, shelters have to be reachable, vehicles have to be maintainable, crews have to be cross-trained. A lunar civilization that treats rescue as its main safety net will discover very quickly that rescue is too slow for many of the emergencies that matter most. Earth can support you. It cannot replace self-sufficiency. And once that is true, disaster planning stops being a special activity and becomes part of daily design. The worst-case scenario starts shaping everything, even when nothing is going wrong. Every corridor would be placed with containment in mind. Every hatch would be part of an isolation strategy. Every rover route would reflect where people can shelter if systems fail. Fuel storage would be placed with fire and blast logic in mind. Medical kits would be distributed based on access time, not convenience. Emergency breathing gear would be stored where people can reach it under stress, not where it looks tidy. Sensors would not just monitor performance. They would watch for the early signs of disaster. Crew procedures would be built around the assumption that a small error can become a large event if it happens in the wrong place at the wrong time. That might make early lunar culture seem obsessive about safety. People may check everything twice, then 3 times. They may care about door discipline and contamination control, maintenance, route planning, battery margins, oxygen margins, seal inspections, and emergency drills to a degree that feels excessive by Earth standards. But that is what the environment teaches. The moon punishes overconfidence very quickly, so safety would not be a corporate slogan or a training poster. It would be part of the settlement's psychology. People who ignore procedure would not look bold, they would look dangerous. That is the deeper point about emergencies on the moon. They become simple in structure even when they are complicated in detail. Pressure loss must be stopped, fire must be isolated, power must be stabilized, injury must be treated locally, a leak must be found, a route to shelter must stay open. There is not much room for theatre because the environment keeps reducing every crisis to the same hard logic. Fix it, contain it, survive it. And once daily life is built around that level of readiness, another realization follows. A place like this would not stay just a survival outpost forever. If humans can endure all of this and still build industry, science and routine there, then the moon stops being only a hostile place to survive and starts becoming something much bigger. The final twist is that living on the moon might end up changing Earth more than it changes the moon. You can spend this whole story thinking the moon is the destination. It is not. The real shift happens when the moon stops being a place you visit and starts becoming a place that supports other things. At first, a lunar base would be mostly about survival. People arrive, stay alive, test systems, measure everything, fix what breaks, and learn what the environment actually does to hardware and to the human body. Early missions would be cautious for a reason. You would not go there and immediately build a new civilization. You would go there to find out which assumptions were wrong. How hard is dust really on seals over years? How reliable is local water extraction? How much shielding is enough? How well do power systems survive the long night? How much maintenance does closed-loop life support really need when it is not a lab test but daily life? But if those pieces start working together, the meaning of the moon changes fast. Once water extraction, shielding, power, mobility, agriculture, and closed-loop life support stop being separate experiments and start functioning as one system, the moon stops being a destination. It becomes infrastructure, and that is the real turning point. The question is no longer can humans live there for a while. The question becomes what happens when a second world starts operating as part of the human system. That is a much bigger question because infrastructure changes behaviour. An outpost is fragile and symbolic. Infrastructure changes trade, transport, science, planning and power. The first time a lunar base can routinely mine water, make oxygen, produce some fuel, repair its vehicles, grow part of its food and shelter people for long periods, it becomes more than a hard mission. It becomes a working node in space. And once that happens, Earth changes too, because now Earth is no longer the only place where human systems run at scale. And one of the first areas where that could matter is science. The moon is not only a hard place to live, it is also a uniquely useful place to observe from. The lunar far side could become one of the best astronomy sites in the inner solar system, especially for low-frequency radio astronomy. On Earth, our own planet gets in the way. The ionosphere blocks or distorts parts of the radio spectrum, and modern civilization fills the planet with radio noise. Signals from communication systems, electronics and broadcast networks make some observations much harder than they would otherwise be. The far side of the moon is naturally shielded from that Earth-made interference. That makes it an unusually quiet place for listening to the universe. That matters because there are parts of cosmic history that are hard to study cleanly from Earth. If you want to investigate the early universe in low-frequency bands, the far side becomes extremely valuable. So the moon is not just a place to put people or machines, it is a place to listen from. A permanent presence there could support observatories, maintenance crews, power systems, logistics, and long-term science in a way that occasional robotic missions cannot always do alone. In that sense, settlement and science may not compete with each other. They may reinforce each other. The same roads, power grids, shelters, and transport systems that keep people alive can also support some of the most important astronomy humanity has ever attempted. Then there is industry, which is where the moon could stop looking like a scientific outpost and start looking like an economic force. Earth is a deep gravity well. Everything you launch from here pays a heavy energy cost just to get started. The moon is much shallower. That fact alone could reshape the economics of moving material through cislunar space. If the moon can provide raw materials, processed metals, oxygen, water or fuel, then some jobs that are expensive from Earth start looking more practical from lunar space. That could include manufacturing certain ultra-pure materials, building large structures in orbit, launching deep space payloads, processing regolith into useful products, and operating fuel depots that support spacecraft moving between Earth orbit, lunar orbit, and beyond. It could also include fabricating components that are easier to make off Earth once the local industrial base exists. That does not mean the moon instantly becomes profitable in a simple way. The engineering is still hard, the infrastructure is still expensive, but once the systems are there, low gravity becomes a real advantage. And that is where the story shifts again. The moon starts as a place where survival is the main problem. But over time, low gravity, local resources, and constant sunlight key locations could turn it into a place where transport strategy changes. A lunar refinery may matter more than another flag planting. A fuel depot may matter more than another symbolic mission patch. A shipyard in lunar space may matter more than a monument on the surface. Once the moon starts helping spacecraft move, refuel, or get assembled more efficiently than they could from Earth alone, it becomes part of a larger space economy, whether people are ready for that or not. And that creates pressure almost immediately, because once the moon matters materially, the argument is no longer only scientific. It becomes civilizational. Who governs a settlement on the moon? Who has authority when multiple national and private bases exist in the same region? How are landing zones managed? How are emergency shelters shared? What happens if one group controls critical water-bearing terrain or key power locations near the poles? How do you separate scientific protection zones from industrial activity? How do you handle accidents that cross the boundary between national programs and commercial operations? What happens when tourism arrives before the legal system is ready? What happens when defense concerns enter the conversation? These are not distant science fiction questions anymore once permanent hardware starts going down. The moon is close enough to matter economically and far enough to create new legal stress immediately. Science, mining, long-term habitation, communications, tourism, prestige, and strategic competition could all overlap in the same environment. That means the moon would force humanity to define what a planetary civilization actually means in practice. Not in speeches, in law, logistics, emergency coordination, resource use, and power sharing. That may be one of the most important effects of lunar settlement. It would force humans to stop thinking only as nations sitting on one planet and start thinking as a species managing more than one operational world. That is a big shift. And that leads to the final answer, which is bigger than the hardware and bigger than the danger. The deepest truth is not just that life on the moon would be hard, it is that it would change the definition of human life. You would not just be taking ordinary Earth life and moving it to a grey landscape. You would be building a new mode of existence. People would live in partial gravity for long periods. They would depend on closed-loop ecologies instead of open planetary cycles. Towns might exist underground or under regolith for protection. Industry would begin using extraterrestrial materials as normal inputs. Timekeeping would be artificial. Medicine would always track radiation and gravity effects. Psychology would have to adapt to life where Earth is visible but unreachable. Work, architecture, agriculture, transport and law would all start changing under the pressure of a second world. That is why the moon matters so much. Not because it is easy, not because it is nearby, and not because it is some simple stepping stone. It matters because it may become the first place where humans prove they can build a lasting life outside Earth's natural support system. If that happens, then the moon is no longer just a hostile place that human has learned to endure. It becomes the first proof that human civilization is no longer locked to one planet. And once that proof exists, Earth changes too. Economically, strategically, scientifically and psychologically, everything changes. Earth stops being the only centre of human life. It becomes the first centre. That is a very different future. So the final twist is simple. Life on the moon would be dangerous, exhausting, technical and psychologically hard. But that is not the biggest part of the story. The biggest part is what comes after humans learn to make it work. Because at that point, this stops being a story about surviving on the moon. It becomes a story about whether humanity has finally become a multi-world species. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.